Good afternoon, everybody. Thanks for coming to the session. The session is Deep Dive on Amazon EMR, Best Practices and Design Patterns. My name is John Fritz. I'm Senior Product Manager for Amazon EMR, and I'm joined by Naveen from Asurion, who's a Senior Principal Architect. Actually, before we get started, how many people here run Hadoop or Spark by a show of hands? Fair amount, that's good. How many folks run it on AWS today? A fair amount. And then how many folks in the audience run it on EMR? Great. So real quick, we'll go over an overview of the presentation. We'll start out with a quick overview of the Apache ecosystem available on EMR. It might be a refresher for some of you who currently use it, but we'll go through that quickly. Then we'll talk a little bit about using EMR with S3 and other AWS services. Just a quick overview on kind of just a common practices on how people are connecting these Hadoop applications running on EMR to the various data stores in AWS. Then we'll go over a few slides on just some best practices around securing your Hadoop stack, both from an IAM perspective, an application auth perspective, and an encryption perspective as well. And then a quick end on lowering costs with auto-scaling, which is a new feature that we launched a couple weeks ago, and spot instances as well. And then I'll hand the mic over to Naveen, who will talk for about the second half of the presentation on building a data lake at Asurion using EMR, S3, and a variety of other services. If we have any time at the end, we'll take a few questions. So here's a quick graph. We actually update this diagram every time we do a release. We release a new version of EMR around every 5 weeks or so, showing actually from about a year ago, EMR 4. We relaunched with EMR 4.0 and had 4 or 5 applications. Fast forward a year with EMR 5.2, which we released last week, or 2 weeks ago. And we've got, I think, over 15 open source projects, and typically the latest version of each. Actually, with Spark, we were a couple days behind the Spark 2 release. Spark minor versions as well, we're very close behind open source. But for those of you who don't use EMR, a quick kind of view of how we think about the stack of applications we have. At the base layer, we have the data stores. Typically, customers are using Amazon S3 as their input and output data set. We'll go over that a little bit more in detail about why we see that in a bit. But we still actually install HDFS on your clusters as well if you needed to, say, store some temporary data or had a reason why you needed to store data locally on the cluster. From there, we use Yarn, and we install Yarn. And actually, the EMR cluster is made up of core nodes and task nodes and the master node. A core node runs node manager, some of the other daemons, and HDFS data nodes. The task nodes do not. So it makes it easier to scale up and down, where if you do have data in HDFS, you don't have to deal with data node rebalancing. We also have hbase, NoSQL on Hadoop, and Phoenix, which is SQL over hbase. If you needed, say, a SQL interface over your data in hbase, that doesn't run on Yarn. And the same thing with Presto, which we typically see customers using for low latency SQL on S3. And actually, for those of you who don't know Presto, it was born out of Facebook. Netflix, I think, has a presentation tomorrow talking about how they run a 25 petabyte data warehouse using Presto. It's a very powerful tool for low latency SQL. On top of Yarn, we've got a bunch of frameworks as well that utilize Yarn for resource management. We have MapReduce, which is still people using, but it's more of a legacy application, but more for batch analytics. Tez, which now is the default for Hive 2 on EMR 5. Tez is creates a DAG instead of using MapReduce specifically, and gets better performance, utilizes memory and Tez sessions a little bit to improve performance on, say, faster jobs without a lot of spin-up time. Spark, which many of you guys, it seems like, are running today for in-memory, machine learning, that sort of thing. And then we actually just released support for Apache Flink about a month ago. And Flink is a newer stream processing framework. People who have been running Storm, it's more similar to a Storm-like experience. You can we process every record. You can do some cool things about if you get out-of-order events, changing it by event time, and other things like that. It actually has a great batch interface as well. So we're excited to see that application grow, and we have it today. And then on top of that, obviously, you have Hive, Pig, Spark ML, Spark SQL, Spark Streaming, and all of that on top of those other frameworks. Also would be remiss not to mention we have a bunch of UIs, and actually we'll talk about that in a minute, some of the UIs that are available on the cluster. So here's a quick diagram of Yarn. So I've mentioned Yarn is a core resource manager for a lot of the apps we have on EMR. In this diagram, you can see this is how Yarn might run a Spark application. And we like Yarn because you can run a variety of different frameworks on the same cluster if you say you have a multi-tenant use case. And Yarn does a really great job of managing all of those different applications, trading off resources between the two, and then runs containers on all the slave nodes with the right processes. For Spark, it would be executors. For Tez, it would be Tez containers, and so on and so forth. Also, Yarn supports Kerberos, so you can enable Kerberos on those clusters. A deep dive, Yarn has a bunch of different schedulers. By default, EMR uses the capacity scheduler. Now, we have one queue by default, so when you submit a job, EMR will bring it into that queue and run it. However, let's say that you had a bunch of different types of workloads, and some were high priority and some weren't. You can portion off different resources on the cluster for different queues and priorities of each queue to say, look, if a job comes into this queue, give the resources to that job, take them away from somewhere else. But you can adjust all these settings, and actually EMR has an easy-to-use configuration API where when you create a cluster, you can specify the configuration file and the key value pairs to overwrite. In this case, it'd probably be in core site, where you can change the different schedulers, specify the different queues that you need, and then create a cluster with those configuration settings. I mentioned there's a lot of on-cluster UIs, and they're all available on the master node. By default, the EMR security groups, which are your firewall settings, turn off all the ports except for port 22 to SSH. So you can SSH the master node, use port forwarding, and have access to a variety of different UIs. Actually, I'll show a few in a quick demo in a minute. But you have Hue for browsing the Hive metastore for your tables. There's a really good SQL notebook in there, SQL editor. You can create DAGs of jobs with Uzis and have a nice display showing the different parts of the DAG. And just a great way to have a nice front end if you don't want to use the command line. We also have Zeppelin, which is a rich notebook as well, very common for Spark users to be able, and data scientists, to write notes, save them in Git, restore from other notes, and that sort of thing. But for, say, the admin role, somebody trying to debug jobs, monitor and that sort of thing, the Spark UI, the Resource Manager UI, the hbase front end if you want to see how your region servers are doing, or your cache miss ratio, that sort of thing. Tez to go see DAGs that might have been run by your Hive job using Tez, and even Flink showing kind of a logical view of what's going on during an execution path. And if none of those really meet your use case, you can even bootstrap applications on. Bootstrap actions can be specified when you're starting up a cluster, and they run before we start any of the daemons. So before Hadoop is installed, before anything's installed, we'll run all of your scripts, and we actually have on our AWS Big Data blog some information on how to install things like Jupyter, RStudio, and some other things as well. You have root access over all the machines, so if there's a library that we don't have or a application we don't have, you can install it yourself. This is a common view of having EMR being able to access data in a variety of different data sets. It's very common for complex analytics pipelines to have maybe your cold source of truth in S3, but you might be pulling in data, say, from DynamoDB, or streaming data in from something like Apache Kafka or Amazon Kinesis, or creating, say, search indexes in Elasticsearch. And with all these different applications in EMR, you really have all of the open source connectivity to all of these different storage services to be able to join data, say, across two silos to enrich both, or maybe run analytics on top of many different data stores. In this case, actually, EMR recently open sourced our Hive DynamoDB connector, and you can find it on the AWS GitHub. You can also use it with Spark, so you can create an external table, but specify that external table over a DynamoDB and query data or load data directly from Hive or Spark SQL into DynamoDB. One thing to take note, though, is that the read capacity, because keep in mind you have many different cluster nodes accessing DynamoDB at once, to not get throttled or get the performance you need, you might need to bump up the amount of read capacity. But it doesn't end there. You can use Scoop on Amazon EMR to query data out of RDS or Aurora if you need to, say, pull data out of an operational database and put it into something like a data warehouse or your data lake in S3. You can actually build Elasticsearch index using Hadoop tools and just load them into Amazon Elasticsearch or Elasticsearch on EC2. Redshift supports an open source package in Spark called the Spark Redshift Connector, utilizing basically a Redshift export to S3 and then loading back into your Spark job. Many different tools integrate with Kafka and Kinesis, Spark Streaming, Flink. You can pull data off of those and do real-time, near real-time stream processing. And then finally, Amazon S3, which is our durable object store. And actually, I'll talk about that in a minute. But one example here from a customer use case is Hearst, who's using a variety of different storage systems and kind of using EMR as the glue between all of them. In this case, Hearst, a large media company, over 200 web properties, they really want to understand how their customers are interacting with those web properties and doing recommendation engines, analytics on that data. So they collect all that clickstream data and they push it through Amazon Kinesis. And they're running a Spark streaming cluster on Amazon EMR. In this case, pretty large micro batches of 5 minutes, but still faster than your typical offline batch processing, to roll up that information and then write it out to S3 in JSON or CSV. And actually, they're running more complicated analytics, but also you could use something like Kinesis Firehose to get the data directly into S3 if you didn't need a full Spark streaming job to process that data. Once the data is in S3, they use Amazon EMR once again to pull the data out of S3 and then use the Spark Redshift connector to load into Amazon Redshift and also to load that data and ETL it, transform it, and load the indexes in Elasticsearch as well. So Amazon EMR in this case almost serves as the glue between many of these AWS services to stream ingest and then store in an optimized search or data warehouse, but also in and of itself is doing some processing and analytics work as well. One tip, I guess, with Amazon S3, and Amazon S3 designed for 11 nines of durability, very scalable, low cost, and is really the core idea of decoupling your storage and compute, which my guess is many of the EMR users here are doing this today. It really gives you the flexibility of not managing your data layer. So managing a very, very large HDFS cluster can be very painful. Also, it's in a single AZ. S3 is available across all AZs, meaning you can spin up a cluster in any AZ in the region and access that data immediately. Also, it allows you to shut your cluster down. We found that a lot of folks running Hadoop on-prem have sized their cluster for HDFS. You need all of your data nodes live to get access to data, but oftentimes the compute cycles are idle. It's just holding on to the data that you're warehousing. So we found that you can shut down your cluster when you're using Amazon S3. Your data is still durable and available. Within a couple minutes, you can get another cluster back up and process it when you need it. However, you can also have your cluster on all the time. So it's really up to you from a cost perspective of what makes the most sense based on your jobs. One thing you can do, though, if you're turning your clusters up and down and you're, say, using something like Hive or Presto, which need table schema stored in the Hive metastore, is you can use something like Amazon Aurora or RDS to store that table information outside of any one cluster. So when your cluster comes up, you point it at that database, and you have your tables back. You don't need to recover all of your partitions every single time. And actually, there's a big data blog post or something in AWS Labs that utilizes AWS Lambda to update your partition information, assuming that new data comes in and you haven't loaded it into a cluster. So if you have no cluster active, you can use Lambda to add new information to the metastore asynchronously from any cluster. A couple of S3 tips. You want to avoid key names in lexicographical order. Like say you have time series data and you're scanning everything through a month. The date times are the same. The reason is to improve throughput performance. S3 will store things that are lexicographically similar, kind of more grouped onto similar machines. If you have a more diverse lexicographical key name for the object, it'll distribute it across more machines. You'll get better list performance and better throughput. You can use hashing techniques to do that. Some people flip the date time around and other things like that. So common queries will have better performance. Obviously, compressing your data set will make a difference. You need to have one that's splittable in the right way or have the right object size, but you're minimizing the actual amount of data transferred from S3 over to the EC2 nodes in your EMR cluster. And also one thing we found is that people are commonly using Parquet, assuming that you don't need to migrate your schema often and that your queries can leverage something like a columnar or file format for performance because you've got a wide table, you don't need to access as much data. The less data scanned, obviously, the better performance you're going to get. One new thing about S3, and actually before when people were running hbase, they'd run hbase, they'd run HDFS on cluster and have these large hbase clusters primarily sized for the data stored. Last week we launched support for hbase using S3 as a data store. So your hbase root directory where you would have, say, the H files, the data in your table, some additional metadata, instead of storing it on S3, or sorry, in HDFS, you're storing it on S3. What that allows you to do is size the actual cluster for the amount of compute and memory, because the region servers will cache some of this in memory, that you need for performance reasons, not necessarily sizing a large cluster. And because HBase can store a lot of data, it's very scalable NoSQL, a lot of times your cluster size would be very massive for the amount of data stored. But a few things we do to increase performance, because when there's a cache miss on a read, HBase is going down to S3, and the random I/O performance in S3 is obviously not as good as an SSD, is we will cache using the HBase bucket cache as much as we can on the local disk of each node. And so typically, and actually on the next slide I'll explain more of Finner's use case, but it's almost you have a tiered storage. You have the option of saying, well, I don't really need the fastest performance on 2 petabytes of data, so I'm not going to cache everything. I'll cache kind of the warm working set that most of the reads are accessing, but when there's an outlier, I can take a little bit less performance, but pay substantially less. So we have that caching going on in the background. You can also shut down your HBase cluster and restore it, or in a DR scenario, let's say that you needed to move your cluster to another AZ, because all of your data is already there and durable in S3, you can shut down your HBase cluster in one AZ and bring up another one and have a recovery time of minutes, which might typically take days. And a great example of that is FINRA's use case. They actually posted a blog post on the Big Data blog talking about an application they built on EMR with HBase on S3, stores around 3 trillion market records, and they put about 1 billion of it in each day. And they'll go in depth about this. They actually have a presentation tomorrow. I highly encourage you to check it out. They'll go into more detail than I will here. But at a high level, they were running this cluster using HDFS, and they managed to save 60%, which is a significant amount of money with the size, a 700 terabyte cluster, by taking the data in S3 and in HDFS, moving it to S3, running HBase on EMR, and decoupling the storage and compute. In this case, they're bulk loading with Hive, and then doing random reads on this data to back an interactive application. Shifting gears from talking about S3 as a storage and some of the other storage layers you can access in EMR, talking a little bit about security. You can run EMR in a private subnet, and we see this as a popular way to deploy EMR. Customers in that case will use a S3 endpoint in VPC, so the cluster can access the data in S3 directly from the private subnet. And if you have to access, say, things that have public endpoints, like, say, using Hive to query DynamoDB or retrieve an AWS KMS key, any endpoint that's not in a private subnet, you'll need to use something like a NAT or a managed NAT to be able to access that range. A new feature we actually just launched 2 weeks ago is support for fine-grained access control by cluster tags. Today, when you create a cluster, you have a service role, IAM role, that you give to the EMR service to have permission to, say, create EC2 instances, terminate the instances when your cluster is done, and then an instance profile that you put on each node that gives each node in the cluster, like a Spark executor when it calls out to access data in S3, those permissions. And that already existed, but what we allow now is in a policy, an IAM policy or an IAM user policy, to have set a condition on EMR APIs in that policy of grant or deny depending on where there's a cluster tag. So you can create a cluster and actually enforce a user to say when user A creates a cluster, it must be tagged with user group analytics, and that cluster's created. The user can't remove the tag, and then only a certain set of users would be able to, say, add nodes, delete the cluster, add steps or units of work. Any of the EMR APIs that involve in the cluster interacting with the cluster, you can limit by cluster tag now. But even furthermore, that's kind of more of a cluster level security way of doing things. But oftentimes you might have a multi-tenant cluster with many users interacting with, say, Hive. You have a bunch of analysts. Some analysts have access to table A. Some might have only access to table B. And you want to control everything through the gateway point. And so this slide right here, and actually this is going to be, it's a little bit ahead, but in the AWS Big Data blog, we'll be posting more information about how to do this. So this is a little bit of a preview. You can do this by configuring Hive Server 2. There's a bunch of ways, but this new blog post talks about using Apache Ranger, which is a open source project that's almost like a policy generator and enforcer for many of the Hadoop ecosystem applications. In this example, you can use something like Q, and you can do this today, and link up Q using LDAP to, say, your Active Directory to get all of your users. So when a user comes to the terminal, they can log in as themselves. But then the new thing is using a CloudFormation script from this blog to install Ranger on an EC2 instance and then have Hive Server 2 and HDFS in this example interact with that, the policies that you've created in Ranger to say, if I've logged into Hue as user A, can user A access this table or not? And actually, if we could switch over to my computer, I can show you a quick preview of what some of these things look like. So here I've set up Hue just like that was shown, communicating with the Active Directory, and hopefully this will log in. There we go. And for those of you who don't know Hue, it's a very useful tool. You have a robust SQL editor. You can go browse tables. In this case, there's a table with some sample data. You can actually have a nice preview of what some of that data is, so it's great for analysts and writing ad hoc queries. But there's two tables in the cluster. There's Table Analyst 2, which I logged in as. Table Analyst 1 you can't see, which is by design. But if you run it, it'll call out to Ranger and see if I have access. In the end, I'm denied. From the Ranger view, and the Ranger UI has a rich UI where it actually uses Solr on the back end to process basically your audit trail, so you can go as an admin user in Ranger see who's been accessing what. And then here, as you can see, it might take a minute to refresh, but earlier I was doing it. You can see here who's been denied, who's had access, and then from the access here, you can control all of your policies with a rich UI here. And as you can see for Analyst 2, I don't have access to Table 1, and I was denied. So it's a very, very nice way, and we can switch back to the slides. It's a very easy way to manage a lot of policies for Hive, and they're rolling out more and more support for more applications as well. I've got to race through the next slide so I can hand it over to Naveen, but I do want to mention that we support now encryption for Tez, Spark, and MapReduce. And we make it easy using a feature called security configurations, where, and here's a screenshot from the console, you can select the AWS KMS keys you want to use, or you can provide an encryption materials provider with information on how to say access keys from your HSM or custom keys, and can save this configuration with us and then reference it when creating a cluster. And before everything starts up, we'll encrypt all the local drives using Lux. We'll configure encrypted shuffle for Spark, encrypted shuffle for Hadoop and Tez. And then with data in S3, we'll configure EMRFS, which is, as I mentioned before, our S3 connector, to be able to interact with data in S3 that's encrypted client-side or server-side using KMS or S3 managed keys. So if encryption is important, also EMR is included under the list of services that are HIPAA eligible in AWS. So if this is interesting, happy to talk more also after the presentation. But all of this is available today. And an example of that is NASDAQ. They presented this presentation actually at reInvent last year. They have a federated data lake over Amazon Redshift for a subset of aggregate data that's more hot, that is using the very powerful performance of Redshift. But then using Presto and EMR, which is still fast. It's not quite as optimized for a lot of complex joins, but still useful for low latency SQL on a data lake that's all of their data. And it's a little bit easier to store at low cost, because S3 is designed for low cost. And they can shut their cluster down when an analyst, say, needs access to all the historical data. Sometimes they can fire up a Presto cluster and give that analyst SQL interface over that data, then shut it down and not pay for it. But in this case, the presentation goes into more on how they manage a bunch of custom keys to use with EMR, because they client-side encrypt all of their data in S3. So shifting to the final point that I want to go through is autoscaling and Spot. EMR shipped support for autoscaling 2 weeks ago, and it's available in most regions, and we'll be rolling it out to more regions in the next couple months. Basically, EMR sends metrics to CloudWatch today, Yarn metrics. And we actually have a few new ones like Yarn percentage used memory and container pending ratio, just metrics that have to do with how much is my cluster being utilized, and if I added more nodes, would I actually have any extra capacity. That gets pumped today, and behind the scenes, EMR is configuring CloudWatch alarms and using application autoscaling to when you've set a policy saying when Yarn memory is utilized 80%, add nodes. EMR will go through that and then add nodes to your cluster. And applications like Spark with dynamic allocation will take advantage of the new nodes that come up and scale those applications out. The same thing for going down and decreasing the cluster size. And actually, with this new feature, we have two scale down behaviors. The default one now is we won't scale down your cluster until it's nearing that instance hour boundary. You've paid for the hour for the instance. Having it around for longer isn't going to hurt, and maybe a new job will come in that'll utilize that capacity. So we've instrumented logic in to not actually terminate the instance until it nears that hourly boundary. However, we also have behavior to say, don't terminate the instance unless all Yarn containers are done running on that node. And then we'll blacklist the node and drain off the work, and eventually nothing will be running and we'll shut it down. So you have more of a kind of cost optimized scale down and a workflow, don't lose any running tasks option as well. And finally, before I conclude, I want to announce that we're going to be coming out soon with the feature Advanced Spot Provisioning. And that'll be available soon. What it'll allow you to do, it has some kind of flavor of the Spot Fleet feature set, if anyone here is familiar with Spot Fleet, and support for spot blocks as well. It'll allow you to specify a set of instances to choose from with a bunch of different bid prices, also several different AZs, and based on the capacity of those instance types in the AZs and what's available for the lowest unit cost, EMR will provision a mix of these instances to give you the lowest cost cluster in the AZ with the most available capacity to avoid any spot interruptions. Also, spot block support. If you know that your job, say, takes 4 hours, you can specify a spot block and not actually get that data interrupted. So anyway, I'll hand the mic over to Naveen to talk a little bit about how they built their data lake with EMR at Asurion.
Thanks, John. Hey, I'm Naveen from Asurion. Today, we're going to focus on how to leverage Amazon services to build a data lake that with a single unified data lake where you can support your today's kind of analysis, where you have traditional BI users, report users, data scientists, at the same time, keeping the cost and security in mind. How many of you guys know who is Asurion? So, Asurion is the leader in providing customer support, and it's a leader in production services. So when you guys have your devices, and if it has support and warranty, that's what Asurion provides. Today, as you can imagine, when you guys lose a phone or some kind of electronic device that you're attached to, it's quite a hassle to get back to your contacts, your photos, and all of your social media content. So Asurion basically helps. Our goal is to make technology seamlessly work and make our customers have lives richer. So Asurion supports almost 290 million users globally, and we have a constant innovation that happens at the Asurion, and we are global in US, South America, Europe, and Japan. Asurion has a wide variety of data sources, ranging from OLTP applications to unstructured data from telephony, voice to text, claims data, nodes, and social. With 290 million customers and over 10 billion interactions and 52 million interactions for voice and 24 million claims and unique visitors, we have a huge volume of data, so which comes down to the typical challenge of the volume, velocity, and variety. When we started this project back in 2015, our data growth was data size at the time was around 1 petabyte. So in the last year and a half, we have actually grown it to 3 petabytes, and we expect the data to be grown to 8 petabytes. So with this expectation of data growth, what we are trying to have is how do you define a single unified platform to support today's users, especially analytical users. So for which, what we have laid out is some core fundamental principles that would help and guide us while building our data lake and provisioning it to our end users. One of the guiding principles that we have embraced is to store all the enterprise data in one single location. So what this enables us to do is to reduce the data proliferation, and it reduces the data footprint for the data exposure or data breaches. Other key area, one of the principles that we have leveraged is to provide the data as quickly as possible to analysts or data scientists to do data discovery and data analysis and provide value or actionable content or information from the data. So for which we have embraced ELT as a pattern rather than the traditional ETL pattern. And data quality is a key because we have to build trust in the data that we have. So what we recommend is to handle data quality and data security from get-go when you're designing your data lake. Data security is also a key foundation. With the recent changes with Brexit in EU and now LinkedIn now being banned in Russia, security policies are constantly changing. So have enough metadata attached to your data. When policies change, you can embrace that, and instead of rebuilding your data lake, you can just configure your data lake to meet to those local security guidelines. We talked about velocity and variety. And one of the things that we wanted to embrace is, with the recent world, with the recent changes, how things are moving towards the market with MVP and agile way of building products. Scale is very important for us because an MVP can be successful in a market or cannot be successful in the market. But if it is successful, how do you scale that thing without having to invest your lot of money in infrastructure, your capital investment in infrastructure? So we wanted to have a system where we can scale on demand without manual intervention. Another thing is we would like to have the cost to be minimal, so we would like to do it as a pay-as-you-go model. To keep all of these things in mind and to keep our operational costs lower and to support the business agility, we have chosen platform as a service as our core foundation to our architecture. To solve the challenge, we have chosen this as our logical architecture, where you can see on the left-hand side all of our OLTP systems where we can produce the transactional data in the traditional relational databases, or even like events coming from your devices, and also even from the social media events. So we take the data and we have a data extraction layer or data service layer where we collect through a standard interface of odbc or jdbc, or a change data control or change data capture like SQL Replicator or Oracle Golden Gate, tools where you can extract the data and encrypt it, especially when moving the data into the cloud, and it could cross a country boundaries. So we'd like to make sure that we are securing the sensitive information. So we encrypt the sensitive information and then load it into our data lake. So in data lake, where we have S3 as our central hub, where we persist all the data, and we use EMR to process the data to make that raw data to be meaningful content or information. Once the processing is done, we take the modeled data and pump it into optimized data sources. In this particular scenario, we are using Amazon Redshift and DynamoDB based upon the use cases. And the other layer that you see on the right-hand side is your data virtualization layer. We use this as a single unified layer to control access to the users. Basically, we authenticate and authorize the users as a single layer, rather than configuring security at each of the product level. SQL Server has its security, Oracle has its security, Redshift has its security, so things of that nature. Instead of configuring security at all of these places, we have chosen a perimeter configuration. So we encapsulate all of the data around data virtualization and configure security at one single place. And that's your traditional BI reporting tools. Any tools which supports JDBC, ODBC, or REST API can be used, like ClickView, or Tableau, or Spotfire, or QuickSights. The bottom you see is our enterprise orchestration layer, where we use this environment to schedule the jobs within our ecosystem to transform the data and move the data across the different data sources like Redshift and SQL servers or Amazon RDS. On the top, you see an environment where we have created to support traditional test data management. In today's world, when you do your ETL work in SQL data warehouses or Oracle data warehouses, you have production systems, then you have dev systems and QA systems. Most of the time, people spend quite a bit of time trying to generate the test data to move the data into the lower environments for the development team to build and test. So with help of Amazon EMR and S3 architecture, we were able to mitigate the need for test data management and leverage directly, able to access the data directly from S3 and providing the capability to the users to do their development without impacting the production ecosystem. Here are some of the just overlay of Amazon Web Services icons on of our data lake, what we have been using so far. This is not a comprehensive list. For this particular scenario, we just put a sample set. We use Amazon Firehose and Kinesis Stream for event streaming with the Lambda. We use Amazon S3 for your central data storage, EMR for data processing, RDSs for external metastores and other transactional data sets, and Amazon Redshift for your columnar reporting. And we use Elastic Beanstalk and Elastic Cache to provide APIs from some of the data that has been churned using EMR. So now we talked about just brief overview of our data lake architecture. So in this particular section, what we're going to focus on is Amazon S3. So during our journey, we're going to share some of the key takeaways that we have learned during our journey while ingesting data into Amazon S3. And as typically for all storage systems, we want it to be secure, scalable, durable, and tiered storage. So for that, we have chosen S3. So while we're ingesting data into the data lake, some of the key things that we have to transform the data so that it becomes much more easy to transform using EMR, MapReduce, or even through Spark, especially with the way the 5 different file formats are available, and some of them are splittable, some of them are non-splittable. So some of the key takeaways that we have learned during our journey was to handle carriage returns and line feeds in the data that you have so that it doesn't become a split record and the MapReduce doesn't treat it as 2 different records to process it. And we also chosen a specific delimiter and removed the delimiters from the rest of the text. And other key important thing that we have learned is how do you handle time? We have servers in all over the world, and each one has its own local time zone. So before we ingesting the data into the data lake, we have chosen to convert it into UTC. As a single time zone. And other thing is based upon the MapReduce containers and the size of the nodes that you use and the amount of memory that is available on it. So file sizes are very key. Otherwise, you're going to get the splits, or it's going to wait for resources, or you're going to get memory overflow with the JVMs. So what we have done is while we ingesting itself, we are able to split the files at 128 meg. So we recommend anything greater than 128 meg and 512 meg of a file size, compress it using gzip or Snappy is one of the key things that we have learned. For performance and for data scanning, it's better to always have a partitioning strategy in place where you can choose to partition your data based upon your business activity date or whichever is meaningful to your data set. And the other thing is that on S3, the object path is case sensitive. So if you have multiple developers developing it, so we would like to convert it into one single case, either convert it to uppercase or a lowercase. So we have chosen to convert it into lowercase. So now we know how to get the data into the data lake. What are the transformations that we need to do to get it for the data to be transformed to get it into the data lake. So we have used Python libraries to push the data from on-prem to AWS S3. We have leveraged the multi-part upload strategy, and while loading the data into the data lake to make not all data is equal, right? So some data is much more valuable than the other data. Some data is accessed more often than the other. So we have different classes in Amazon S3. So one is the standard storage, one is reduced redundant storage, other is infrequent access. So you can choose to set those settings while you're doing the upload process. And you also have the lifecycle policies enabled so that you can move the data from a higher cost storage to the lower cost storage from standard to infrequent access once the data is processed. And the other thing is on S3, one of the recommendations that we have is keep your storage and compute as close together as possible. So we don't want you to guys launching an EMR cluster in EU and keep the data storage in US. So that gives you better performance if you keep those things local together, and the cost will also be much more economical. One other thing we have also noticed is on S3, you have a throttling of 100 puts, deletes, and gets, or 300 gets. So when you reach that later, you have an option to either expand or to request for another bucket, and you can partition the data for those buckets. And always tag your things so that you can know how to track your cost. And for S3, You can also have IP restriction policies where you can say it is bound to certain IP. You cannot access it from any other IP than your organization IP range. And you can use the IAM and ACLs to control the security on it. Oh, did I go up? Sorry. So now we know how to get the data into the data lake. We have put the data into the data lake. So once we wanted to put the data into the data lake, we needed to have some kind of a logical structure how to organize the data in the data lake. For those things, what we have defined is basically 4 logical layers of data. So in layer 1, what we are calling it as raw data, where you keep the data as a raw format as much as possible with minimal amount of transformation. So it becomes our system of truth and does the basic minimum encryption for your sensitive data, transform your data, gets it into the data lake. Layer 2 is basically taking the raw data, applying your quality rules, and transforming the data to a different partitioning strategy that's much more faster and economical for your analysts to use. So in raw data, in layer 1, you would like to choose a partition strategy that would be much more economical to handle your ETL daily deltas. But in layer 2, you might be choosing a different partition strategy based upon what kind of queries you're running. So in layer 2, we have chosen ORC and Parquet as our file formats. In layer 3 is basically taking all of these OLTP system raw data sets and then trying to model them using a Data Vault 2.0 pattern. So it's a standard pattern available. It's similar to your star schemas in the traditional BI model. So Data Vault helps us with EMR that's much more optimized to process the data, where I don't have to process all the facts before the dimensions. So in layer 3, we choose ORC as our primary format for people to query the data. And we also choose text to write the final output. So we use this data to push the data into Redshift if some of this data is required to be much more SLA bound. And the 4th layer is basically a reference data, which is basically a confirmed dimensions or master data. And we use ORC as our file format there. Now we have the capability of getting the data, storing the data, and we have logically organized it. Now we would like to see how we can process the data. So as Jonathan has talked about, those are the best practices, right? Have a single meta store for all of your data so that you know where your data is located, what is its structure. You can have transient clusters or long-running clusters. And all the clusters, you can have more than one running cluster at a time, and all of them can be looking at the same S3 objects. So what happens with this is you don't have to duplicate the data. The data stays at one single copy, reduces your cost, and with the transient clusters, you can compute and then shut it down as soon as you're done. Amazon EMR supports much more applications than traditional MapReduce. It supports Tez, Spark, and one of the applications that it also supports is Presto. Presto is used for our ad hoc usage for doing some query analysis. And in this slide, we would like to key attention to why we have a second meta store for Presto, and we'll go in details of why we have to do that. So at this time, with this particular basic core fundamental architecture, right, with Amazon S3 for your storage and EMR as your compute, we are able to deploy this particular pattern at Azure in US, EU, and Japan. And some of the stats that we have is more than 50+ business analysts and report users are querying the data from our data lake. We have more than 1,000 ad hoc queries runs per day. And we have 20+ sources of data in our data lake. And 100+ of ETL Hive jobs run every single day to convert the data from raw data to quality or modeled data. And we have more than 25+ Spark jobs to run some of the, what we call like churn prediction or lifetime value for some of the analytical needs. And we have more than 2+ petabytes in our data lake. In the next slide, we'll talk about some of the lessons learned during EMR. So the key thing here is always when you're creating an EMR Hive database, use S3 path. So by default, it takes the master node IP space. And when you destroy the cluster and bring the recluster app in the Hive metastore, you still have the same IP space. So to have some, you will have some issues with it. We have faced some of those issues while we're migrating from one environment to another environment. So we recommend using S3 path. Use external tables, use a single metastore, and you can recover partitions into the data lake from your S3 into Hive Metastore by running a simple MSCK repair command, or you can alter table and add partitions into it. You have 3 different endpoints for S3 normally. One is S3, S3N, and S3A. For EMR FS, we will recommend you to choose S3 by default. If your application doesn't support S3, you can choose S3N. But S3A is not something that we would recommend to use. It's not supported at this point of time. And you have clusters which are transient and long running. We have scheduled our clusters on and off by bringing up and down using Python libraries and our enterprise scheduler. One of the key things about once you have the data, when you process the data, we would like to compress the output. So for the compression, we have chosen gzip as a highly compression, but it's not splittable, and Snappy for streaming data, which has a low compression, but it's a splittable. Some of the key takeaways from Hive is basically partition your data, denormalize your data, enable speculative execution. We have chosen file format ORC. Parquet is also good. ORC for us is much more interoperable. Enable vectorization. Enable parallel execution of jobs. And enable your compression of your intermediate output between MapReduce jobs, between the mappers. And also enable the joins, auto-convert joins. What will enable is if you have a smaller table to join to a bigger table, then the smaller table can be spread across all of the data nodes. It doesn't have to do the shuffling of the data, and it can keep it in memory and get you the results much faster. So now we have learned about processing of the data. Now we have processed the data. Now how do we enable our business users to access this data? For which what we have leveraged is Presto, which is a native application on EMR for low latency queries. Some of the lessons that we learned for Presto was, for us, ORC was much more interoperable. While you're working with Presto, Presto supports predicate push down so that it doesn't have to bring all of the data into the memory. It can say, hey, if I'm looking for certain range of data, it can just look at that partition and get the data back to you. So Presto is way faster than Hive and Tez. It supports low latency queries, and it is a very memory intensive, so we got better results when we used R32X large as our machine type. And some of the things that we need to watch out when you're doing Presto is when Hive supports bucketing, and Presto still is a challenge with bucketing. Based upon GitHub latest articles, the new releases are going to support bucketing. But as of when we were working with it, bucketing was a challenge. And Presto was not able to handle complex data structures like maps that you can define, or structures that you can define in Hive. So Presto was having a challenge. But most of those things are getting resolved. And other thing is when you're doing huge data set joins, based upon your node type, how much memory you have, the joins, there is a memory limit how much you have. So an R32X large, I think it is 30 gigs of your memory. If your data size exceeds more than 30 gig, then you need to do much more, a little bit more configurations on it. And Presto still has, I mean, with the latest release of Presto, it's been taken care of. But in the older versions of Presto, you have a challenge of mapping the Hive data types to Presto data types. Some of those are like floats, characters, and varchars. Some of the settings that will give you a better optimal results is how much a single query can take memory across all of your data nodes. And what is your timeout of a single query and the age of the query. So age and timeout are the key. If your timeout is lower than the amount of time it executes the query, then you will not get any results. So you need to make sure that your age and timeout are being set appropriately. And also enable, what we have learned is 42% of our memory can be allocated for each query on a given data node. With the latest release of ORC2, or with the latest release of ORC drivers, the third is we were able to see much more improvement in pushing down with the ORC files of the searches when we are having enabled the Bloom filters and optimized the reader and for the ORCs. So these are some of the key lessons that we have learned during our journey with Presto. And now we'll talk about why we had to create a separate metastore for Presto. As you guess, in the previous slide we talked about, Hive has certain data types which are not all compatible with the Presto. In order to make that change, you have to create, again, a table structure in Hive to handle that, or in Presto to handle that. So what we have done is created an automation routine which takes the Hive metastore, converts the data types, and then puts it into another metastore and recovers all of the partitions from it. So in this case, what happens is if Presto compatibility is not there, those fields will not be available in Presto. This will enable you to get that particular data back. With the latest release of EMR 0.152, most of these challenges have been resolved. So now we'll talk about sandboxes, how you can enable sandboxes for your development resources or QA resources on for your data analysts or data scientists. As we talked before, that in traditional world, you have to do test data management. With help of EMR and S3, we are able to mitigate that challenge. The way we mitigated that challenge here is, in the production environment, we have the production S3 storage and have its production EMR clusters. You see the maroon S3 storage, that is the sandbox storage, which is also on S3 but on a different bucket, and you have each sandbox can have its own EMR clusters. Why do we need to have its own EMR clusters, right? The reason why you need to have an EMR clusters is you can have yarn to configure with your schedules. When users are submitting jobs to the yarn, you have to put in your queue name so that, hey, use this default queue so that I can have these resources. So it was challenging for us to train our users. So we were able to mitigate that challenge by providing each group of users a standard dedicated EMR cluster for them to analyze their own data. And we were able to handle security by having separate metastore for sandbox, one for production and one for sandboxes. And we can have more than one sandbox, and each sandbox can have, all of the sandboxes will have one single metastore, and you can sync your production data metastore to the dev metastore. And from security perspective, you can make sure with the IAM policies, the production S3 to have only read-only, and read-write access to SAN3 boxes. So below you'll see a small script that will help you to create an EMR cluster through command line, where you can set up a policy where you're launching an EMR cluster. At the last line, which is called instance profile, EMR EC2 sandbox 1 role 1. So in that role, you can specify an IAM policy stating that, hey, deny all delete object and put actions on your production bucket. So that makes your production bucket secure. At the same time, you can have the delete and write objects on your sandbox so that they can have a processed output in their localized environments. Now, with all of the users having their own sandboxes, now we wanted to have a provision mechanism to manage cost, and also they have the ability to scale up and scale down our clusters automatically based upon the workload. So with the latest release of the Amazon EMR auto scaling, it has some of the metrics available in the CloudWatch, as like is the cluster idle, number of containers pending. So those are all out of the box. What we have also leveraged is to create a CPU usage as a custom metrics. And you can also define the minimum and the maximum count of your cluster to scale up and scale down. And when should it occur? When your load is greater than 60% or 80%. So here is the sample graph in working that we were able to using Ganglia. Ganglia is a distributed metrics collector, which is a native application on EMR, where it gives you, based upon your EMR jobs running, what is the load it is taking. And the next graph next to it, which is on the other side of the CPU graph, talks about your map reduce increasing and decreasing based upon the load. So we have, for this particular auto-scaling is done through CPU metrics. So CPU metrics is not available out of the standard CloudWatch metrics. So we have used Ganglia to get those things. In the next slide, we'll talk about how to use Ganglia to get that metrics. So Ganglia has a URL where you can ask in the response and as a JSON, where it gives you the CPU usage by minute. So we take the data using Lambda. We are able to compute the per minute CPU usage, and it's a sample snippet of code where you can calculate the average minute CPU usage. Once you have that CPU usage, you can create a CloudWatch alarm. We were able to leverage again the Lambda to create a CloudWatch alarm to write to CloudWatch as a custom metric of 1 every minute CPU usage. With that, we are able to create as a metric to do scale up and scale down. Here is a sample slide that demonstrates the cost savings that we were able to accomplish. On an average, we were able to get 55% of cost savings with the EMR auto scaling. And that is, we also have reserved instances in this particular scenario, but if you take reserved instances off, you would have 40% of the cost savings. So now we'll talk about data virtualization. So we have used the data virtualization as a single layer where you can configure security. So this security enables authentication and authorizations for the end users. Here is a typical architecture that we have used. We have encrypted all of our data at the field level before putting into Amazon S3. Once we have the data there, we are able to process it and persist in the higher layers. We also have Presto for users to query the data ad hocly. Some of the model data based upon SLAs have been also moved into Redshift. Now you have at two different places the data. Well, some is in S3, some of that is in Redshift. How does a user know which data is where, and how do I do their cross-federation joins? So for which what we have leveraged is a data virtualization layer where you can configure security, authentication, authorization, and do data federation, and keep all of these technologies abstract from the end users, so that tomorrow we might find a new technology that helps us. So we don't want our users to rewrite their code. So data virtualization helps us to write traditional ANSI SQL code. So here are some of the advantages of using data virtualization. So all of the code that you are writing is going to be ANSI SQL compliant, and it can be pushed down to the end sources, so that so for example, if you're trying to get data from Presto, all of the query goes into Presto. Presto does all of the work and brings it back. If for certain reason, if you want to do data set joins between Presto and Redshift, so it will try to push down as much as possible to both of those sources, get the final output, and then do the joins as minimal as possible in the data virtualization. So you can also enable column and row level security in the data virtualization. And we can enable authentication against your on-premise or your existing LDAP for compliance. So all the ad hoc queries and reports are through JDBC and ODBC against Amazon Redshift and Presto. So as I was talking before, you don't have to worry about configuring security at multiple sources. Configuring it one, maintaining it one becomes much more economical and feasible. So some of the key takeaways that what we have learned during our journey is manage costs from get-go. So create tags to all of your resources, manage them accordingly, do real-time frictionless scaling using EMR auto-scaling capabilities, align to core design patterns like platform as a service, leverage readily available solutions, then rebuilding those things, and design for security and compliance from start. As we all know, the security is going to change and evolve as the privacy of the people has become much more what I call intrusive, or with the latest changes with Brexit and LinkedIn. And fail forward and adjust as needed, and harden your solutions in one marketplace and then deploy it into other market spaces. With this, I'm going to hand it over to Jonathan.
I just want to say thanks, everybody, for coming to the presentation. Remember to complete your evaluations. We'll be here to take some questions afterwards as well. Thank you.